Hi, this is our third episode, the last one, and you called it What Are the Numbers Telling Us? We are interested in the amount of time added to the terrestrial days since the formation of the moon. Then we have this calculation here. We have to multiply the rate indicative of the day's lengthening uh, times time elapsed since the beginning of the phenomenon. We are talking about this phenomenon that makes moon going further away from Earth each time, and at the same time, the day is lengthening on Earth. And we have two hypotheses we already talked about there. Then the first one, this rate that is connected to the lengthening of the day, that indicates the lengthening of the day, would be constant since the beginning of the phenomenon. And the other one, that is the real thing that is happening. But let's make the exercise with the first one, calculating the area below the line. So the line here is close to zero because it's um, 2 milliseconds per century, the rate today. And if this was the rate since the beginning, and we already see this, that it's not um, um, valuable for the time of the moon's formation because the amount of time would be extremely high. So we started from 1 billion years after the moon's formation. And imagine that after 1 billion years after the moon's formation, started this phenomenon, which main source is the gravitational field, the moon and earth gravitational fields together. And it makes the tides and it makes this phenomenon happening. So we have to multiply the rate with it, which is 2.0 times 10 to the power of minus 3 uh, seconds per century, times 10 to the power of minus 2, because we're talking about years, times 3.5 times 10 to the power of 9 years, because we are talking about 3.5 billion years ago. And the number it gives us is 70,000 seconds, 7.0 times 10 to the power of 4. And we know that the day has 86 thousand seconds per day. So it's close, and it would be possible if the gravitational field and the influence of the gravitational field was the same since the beginning, since 3.5 billion years ago. And that's not the case because the moon was much, much closer to us, to Earth. The day would have, in this calculation, 4 hours, 33 minutes, um, 3.5 billion years ago. But that's not the case because the initial conditions 3.5 billion years ago were there. Those ones, the distance between Earth and Moon was 22,400 kilometers. We already said that it would be between 20,000 and 30,000. We took this number here because of one video that is indicated in our last video. The link is there. So the moon would be 16.7 times closer than today, which means that the gravitational force it's connected to the inversely proportional to the square of this number, which gives us 279 times greater than today. This we have to multiply then the rate by this number. So the rate would be 0.002 times 279, which gives us 0.558 seconds per century. Actually, uh, 558 milliseconds per century. So that's the graph. have, and considering that this rate would be inversely proportional to the distance between Moon and Earth, and as Moon would distantiate itself going away from Earth, it would decrease the force, gravitational force would decrease rapidly, and so we would have this kind of line, and this is the function connected to this line here, to this graph, and we have to calculate now the area below this line, this orange line. And for doing this, we have to have 3 points. We have to know 3 points of the line. And we have already two. This one is in the point 1 in here in the abscissas, in axis, extra axis, because we are considering that this phenomenon started 1 billion years after the formation of Moon. So this in 1 billion years after the formation of the Moon, we have already calculated the rate. And today the rate we know that the rate today is 2 milliseconds per century. And the third number is possible to obtain it on our graph. We put here 2.5. It's arbitrary. We chose 2.5 billion years after the formation of Moon, and we obtain 97 milliseconds per century, the rate that time, if our line is not far away from the reality. And that's what we believe until now. So this is our function, and now we have this function applied to the number 1, which means 1 billion after the formation of the Moon, to the point 2.5 and to the point 4.5. So we have three numbers, and the 3 points in the line, and this gives us the conditions to calculate our coefficients A, B, and C. We have to calculate the three coefficients to put them in the function there. So when we put the three equations together, we get the numbers, and then we applied here the numbers at the function. So those are the numbers. And this is our function. And now, in order to obtain the area below the graph, we have to integrate the function. And that's the integrate. We have the integral we have here, and it goes from 1 to 4.5, which means 1 billion after the formation of the Moon to 4.5 billion years after, and it means today. Okay? So when we integrate everything and put this number there, we obtain this. And now we replace here this powers of 10, because we put them out just to make the calculation. Now we have to replace them. We have to come then back to the point. So multiplying this for the measurements and the unities, we have this number of 441 seconds per times 10 to the power minus 3, which means seconds per century, times 10 to the power minus 2, which means transforming centuries and years, times 10 to the power of 9, which means billion years. So at the end, we obtained that if it was the case, in those 3.5 billion years, the phenomenon would have added to the day about 4 million seconds. And that's totally absurd, because we know that the day is 86,000 seconds, has 86,000 seconds, so it's totally impossible. So then we have to ask ourselves, what would be the Earth settings 4.5 billion years ago? Because then this phenomenon wouldn't have happened at all. Okay? So the conditions were very, very different from those of today. So this is the current geodesic radius measures. The radius, because we have two radius. One that goes from the center to a pole, and it's 6,356 kilometers, and the radius at the equator is a little bit different. That's why Earth is not a sphere, but its shape is a geodesic. It's called a geodesic shape. And when did Earth conditions reach the point S? Well, what we are calling point S here is a point when this phenomenon that makes a moon going further away each time from Earth, and at the same time makes the day makes lengthening is lengthening the day, makes shortening the day of the sorry, the contrary, uh, enlarging the day each all the time. So when did the Earth's conditions reach? And this is the point S means, which means a point in the past. There was a point in the past that the conditions were perfect to start this what is happening until today. This phenomenon connected to each other, which the source is the gravitational field, Earth gravitational field and Moon's gravitational field. So, in order to make this point S, to find a reasonable point S, we made this table where we calculate different numbers here, different distance between Moon and Earth here, 22,400 kilometers, 3,100 kilometers, and so forth. And for each distance, we have, according to the rate today and the same calculus, we have the rate that time connected to the distance. Those numbers are one dependent, are interdependent. And then for each of those conditions, we obtain the function. And here, the time of the deceleration rate in million years, which means that where we put the point S. So in our first calculation, we put the point S 3,500 million years, which means 3,500,000,000 years ago, then 300 million years ago, 250 million years ago, until 100 million years ago. And when we put the results of the integral, we have we can evaluate each result. And as we can see here, the only number is less than the number of the seconds for a day today is the last one. This is the only situation that is acceptable. So if the Earth and Moon, the distance between them was 30,000 kilometers, and the point S was 100 million years ago. So from 4.5 million years ago until 100 million years ago, the phenomenon didn't happen. For many causes, for many arguments we can put on the table, we can conclude that until this time, Earth and Moon were not doing the same thing that they are doing today. And we made some arguments in our PDF that we will provide for everybody. So from there, we made another calculations again, but now fixing the point S in 100 million years ago. So we did put here the distance between Earth and Moon, and we fixed the number, that's 100 million years ago, and then we obtain the results here. And analyzing all the data that those calculations gave us, we came to the conclusion of 100 million years ago, and the day around 1 hour and 45 minutes. But we now will think about the consequences, and for doing that, we have to think about the centripetal force. And then we will see Why is it important? So imagine this is the current conditions. The radius at the equator is here, is given here. Uh, and then imagine a person here on the pole, stepped on the pole, and a person here stepped on the equator. So on the pole, if a person is here on the pole, stepping on the pole, and one day this person will rotate uh, and the radius will be zero. This person will only rotate, okay? But at the same time, and concomitantly, the person that is stepped on the equator, this person will, even if this person is not walking, this person will perform an orbit as if it was an orbit around the center of the planet with this radio. So, in order to make a movement that is not linear, we have to have a centripetal force. And this centripetal force is given by part of our weight on the equator. And if we calculate this centripetal force, considering the radio, we will see this is only 0.345% of the weight, which means a third from a third of 1% of the weight, which means almost nothing. So a person goes from where walking, imagine a person walking from the pole to the equator, this person would feel nothing, no difference in his or her weight. But let's imagine that the point S occurred 100 million years ago, and at that time, the day had around 1 hour and 44 minutes. So the Earth would spin very, very, very faster comparing to today. Any animal that would walk from the pole to the equator would decrease up to 75% of its weight. Now it's very, very significant because if the animal went from the pole to the equator, this animal would feel its weight diminishing and up to 75%. So imagine now an Argentinosaurus. This is the one of the biggest dinosaurs have lived on Earth. Its mass is 15 times the mass of the greater elephants today. And let's compare what they had to eat with the elephant today eats. So the elephant today has to eat 160 kilograms per day, and it takes 16 to 18 hours. And what about the Argentinosaurus if this huge animal was living today? If we just put um, the calculus here, it would be 5,100 kilograms per day, which is totally crazy. Because imagine, this animal doesn't have a huge mouth, for example. But people would say, no, 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 but this is not a mammal, and the elephant is a mammal. The elephant has a brain that weighs 4.5 kilograms, and the brain of this animal was very, very small. So it doesn't need the same amount of energy comparative to the weight that the elephant today needs. Okay, but even in considering all this situation, at least 100,000, or at least 1,000 kilograms per day would be necessary. So it seems that it's crazy to think about this animal living in the same physical conditions of the elephant today. But if there was this, our hypothesis is correct, if this animal was living on the equator that time with those conditions, so it will have 75% less of its weight because of the centripetal force. 75% of its weight would be only centripetal force. And it will feel very, very comfortable on the equator, might be. Maybe it was the thing. Imagine the animals that was flying that time, the big insects. Because if they were in our current conditions, it was very hard for them to fly. But if they were in that time in the conditions that we put in our hypothesis, flying was not that difficult again. But the situation would be totally different if the animal migrate from the equator to the pole. And that may be that what happened was with those animals, because the plates that are on the Earth, they migrated all the time. And the consequence is that uh, if the point S was 100 million years ago, from that point on, the day on Earth started to lengthening. And at the same time, the moon was going further away. Okay? So, and we know that the hypothesis is very accepted today that 60 million years ago, something happened on the planet, a huge event, and a collision. And this collision ended more than 90% of the life on Earth. And after that, after 60 million years ago, the nature did not experiment again huge animals like this Argentinosaurus. And we have to take to put in mind that nature was experimenting those big animals since or during 200 million years. So during 200 million years, it was worth having a big body and weight a lot, because it was possible to eat, it was possible to live, it was possible to move, it was possible to fly, because the conditions are very different from today. And that's our hypothesis. The physical conditions are very different. So what about the atmosphere and the waters? Because the atmosphere depends on the weight of the air. And if Earth was rotating faster and faster, this atmosphere on the equator, in the region of the equator, would be much less than the pressure. Its pressure would be much less than the pressure today. And it would facilitate the water to evaporate. So the consequences, the atmosphere pressure at the equator would be much lower than today, and the atmosphere would be much more humid than today. So the air would be very humid. And the frontier between water and air would not be as well defined as it is today. So maybe because of that, the atmosphere was very uh, stressed with many big winds, and that's why it was good to be big, because the big animals had advantage in being big, huh? And animals could easily migrate from the oceans to the land. It's another scientific idea. It's very well accepted that the became life started in the oceans, and then the animals in the oceans migrated to the land. Imagine the situation today. It's very hard for an animal to migrate from the ocean to the land. But if the atmosphere was full of humidity, then it would be more easy. It would be easier than today. Okay? So those are some consequences of our hypothesis. Our hypothesis, we know, it's just a thinking, an exercise of thinking, and then we are inviting people to come in and to make criticism of our hypothesis and make arguments and give us arguments, because we would like to share these ideas and to excite people in order to have a better understanding of the phenomenon. So our hypothesis, we are very aware that this is hypothesis. It cannot be proved now. It needs much more calculations and work to be done. But the window is open for everybody. So thanks a lot for watching.